Hey there, students. Welcome to Psych History 3 Lab, Module 8, where we'll be discussing random coefficients models. So some objectives for today. I just want to do a quick overview of random coefficient modeling. Then we'll do a data set description. Then we'll load in the data, learn to pivot data from wide to long format, which is an extremely important subject when you're working with this type of data. Then we're going to learn how to visualize data, and then we're going to go ahead and model data. So, what is random coefficient modeling? Well, in my opinion, it's the first step to understanding multi-level modeling. And essentially, random coefficient modeling utilizes maximum likelihood estimation. Up until now, we've always been using ordinary least squares for our regression and ANOVA models. So now we'll be using this maximum likelihood estimation. So we need to define two new terms. There's fixed effect, which is something that does not vary over subjects of groups. It's the average value of the slope or intercept. So when you're getting a fixed effect in these random coefficient models, you're asking, what is the estimate of the effect across all groups? And then you have a random effect, which is something that might vary across subjects or groups. And it's essentially saying intercepts and slopes might be calculated for each group or each subject to see if they vary meaningfully. So when you're getting a random effect, you're essentially asking yourself, how much does the estimate for the effect vary across the groups? So the data set that we're going to be using today was provided by Kim Henry here in the psych department, in which the research team is interested if student performance and coding skills increased over time during a coding class. So during each week of the program, all participants completed a coding challenge. Each challenge had a set of coding skills that had to be employed to solve the challenge. But each challenge focused on solving some sort of substantive problem. So that's something like mapping a social network or developing some sort of algorithm. Each student's performance on the challenge was graded by the research team using a valid and reliable rubric able to detect growth and skills over time. Oops. So let's go ahead. We're going to dig into our studio and we're going to go ahead and create our notebook and download our data set. So the first thing we're going to do is create our project, new directory, new project. Okay, we need to make sure to sit in the right directory. Name this module_08. Create the project. Okay, looks like we created it, and we can go and download the data set now. So we'll go to Module 8 Lab. It's the mlmgrow.csv. Open that up. Do File, Save As, Browse. Go ahead and go to your desktop. Go to Psych History 3, Module 8. Save it in there. All right, great. So we've got our data set loaded in. Let's go ahead and create our notebook. I'm going to go ahead and delete all this. We're going to title this notebook Random Coefficient Modeling. And we'll go ahead and create that table of contents. TOC:yes. I'm going to zoom in a little bit for y'all. There we go. And let's go ahead and save our notebook. In this module 8 notebook, save it in. All right, there we go. We got our notebook created. So let's go and see what we got next to do. So next thing we're going to do, we're going to be installing two new packages and loading in some existing packages. We're going to be installing the LME4 package and the LMER test package. The LME4 package and the LMER test are essentially companion packages with each other. LME4 is the one that's going to allow us to do the random coefficient modeling, and LMER test provides a significant value. So if you just have it loaded in with LME4, it'll automatically give you significance values for your random coefficient models. So let's go and do that. Let me go and load up some notes real quick. Okay, so hashtag load libraries, insert a new R chunk. So we're going to do install.packages quote LME4 install.packages LMER capital T LMER test. Oh, and that's going to be in quotation marks actually. Put that in quotation marks. There we go. And then library, LME4, library, LMER test, library, psych, library olsrr, oopsies, library olsrr, and library tidyverse. So we can go ahead and load all that up. It'll take a little while to load because we're installing a couple packages here, so give it some time. Here we go. Installing the lmer test package. There we go. Perfect. I'm going to go and hashtag these out. Don't have to worry about them more, and then I'm going to press load again to get rid of some of that output. Perfect. All right, let's see what we got next. So next thing we're going to do is we're going to go ahead and read in the data set. And notice I'm going to name it grow wide, and there's a reason for that, because we're going to be learning how to convert data from wide to long, essentially. And I'll show you a little bit what that means in a little bit here. We have a few variables here. We have kid ID, which is the student ID number, team ID, which is the team ID of the student, so the students were organized into teams. We have TXCon, which is the treatment condition. 0 equals there in the individual focus condition, and 1 equals the team focus condition. And then we have performance 0 through performance 6, which is the performance on the coding challenge each week of the program, starting at baseline, so before the program even started, and ending at week 6. So there's a total of 7 in total. The scores range from 0 to 10. So let's go ahead and read in that data set. So go ahead and do hashtag read in data. Insert a new R chunk. Okay, we're going to name this grow underscore wide read CSV MLM underscore grow .csv. And that's going to be in quotation marks. I'm forgetting about the quotation marks here. There we go. So we'll go ahead and read that in. All right, there we go. So we got 100 observations of 100 observations and 10 variables. So essentially, what's going to be different is that we're going to be, so this is currently in wide format. As you can see, each participant has one ID number, and then they have 7 different scores for their performance levels. What we're going to be doing is making it so that each participant appears 7 times and that they have 7 performance scores in each row. So this is going to go from 100 observations to 700 observations when we're done with it. And I'll give you an example kind of what it looks like on the next slide here. So this is how our data currently is, and this is how we're going to be making it. Notice how kid ID number 5 has about 7 different ID numbers, and their performance scores are like this. This is going to be really essential because you're most oftentimes, if you ever want to perform this analysis, your data set's going to look like this, and you need our data set to be in a long format. So I figured it'd be good to take the time to teach you how to convert from wide format to long format. I mean, the reason that it's always like this is it's easier to record data this way rather than recording data this way. So it'll be good for your future if you ever want to do some sort of random coefficient modeling or multi-level modeling or repeated measure modeling to learn how to do this type of analysis and convert your data set from wide to long. So this is pretty important what we're doing here. So what we're going to do is we're going to be using a function called pivot longer. It comes from the tidyverse package. And what we're going to do is essentially take that grow wide data set. Then, and I'm going to go ahead and go here, we're going to be using the calls, we're going to be using an argument called calls equals, which we indicate the variables that we want to convert to long. Then we do names to, which is what we're going to name the new column that the names of the new variable goes to. Then we're going to use names prefix, which means that we're going to take away the prefix to something certain to the variable that we're converting to long. So we're removing that perf underscore. And then we're going to change the values of the new data set that we're going to be taking to name it perform. And I think it's going to be a lot more clear. I'm going to explain this little by little when I'm actually coding it in. And then we have to turn the week into a numeric variable. And I'll show you what that looks like as well. So I think it's going to make the best sense if we just go ahead and get started and I show you step by step what's going on with this data set when we use the pivot longer function. So let's go ahead and do hashtag learn to pivot tables. Now I'm going to say we will turn this data set from wide to long. Okay, so we're going to insert a new R chunk. So we're going to name this new data set called grow underscore long, use an assignment operator. We're going to use a function called pivot underscore longer. And what we do is we indicate first what our data set is, so grow wide, comma. Then we're going to do calls equals perf underscore 0 to perf 6 underscore 6. And what this is saying is take the columns perf 0 to perf 6, and those are the ones that we want to download. So with that colon there, right there, it says go from perf 0 to perf 6. You can use a concatenate function and label every single variable if you want to, but essentially because these are in the correct order, it goes from perf 0 to perf 6. We're saying take these and we want to convert these into a long format. Then we do comma names underscore 2 equals quote week. And that means that we're gonna be getting a new variable that's gonna contain the names perf 0 through perf 6, and we're gonna name it week. So I'm gonna go ahead and show you what that looks like. Okay, so let's go ahead and start with this simply, and then we're gonna add some more to it. So we're gonna get a new data set called grow underscore long, which is gonna have 700 observations. Oh, let me see what I did wrong here. Oh, I forgot to put a comma. There we go. Comma, names 2, week. Now we should have, there we go. We have a new data set with 700 observations. So notice how kid ID number 5, and I have this split up, so it's a reduced data set. It goes 5, 10, 15, 20 for kid IDs. But notice how kid ID now has, there's 7 different variables for kid ID 5, and the value, the name of the variable turned into a variable called week, and then the values for each of those is in a data set, in a variable called value. What we're going to do is we're going to go ahead and we're going to do 2 more things. First, we're going to remove this perf underscore from the names of our week variable, and then we're going to change this value name into a variable called perform. So to do that, we do comma names underscore prefix equals quote perf underscore. And what that's going to do, it's going to remove the perf underscore from each of these variables in week so that they'll look more numeric for us. And then that's going to be essential for when we're doing things later. Then we're going to do comma values underscore 2 equals quote perform. And what that's going to do is going to change this values column into a new variable called perform. So we go ahead and run all that, and just think it should run. Okay, great. So we have 700 observations, 5 variables. So a few things happen here. So we have week now, and now we took away that perf underscore there, and it has numbers here located with it. And then that values column is now called perform. Now, one more thing that we need to do. Notice how these numbers are all shifted to the left, and these are all shifted to the right. So this is on the left side of the column while these are on the right side of the column. That's because these are being read as a character variable. If we were to do structure, well, in fact, I can show you. So we do structure, grow long, and our week variable is going to be read as a character variable. As you can see, week is being read as a character variable down here. We want to convert that to a numeric variable, okay? Because it's able to do that. So the way that we're going to do that is we're going to do hashtag. I'm going to write a comment in here and say turn week into a numeric variable. And that's going to help us out for later. And I'm just going to bring that down one more line. And then to do that, we do grow underscore long using an assignment operator, mutate grow underscore long, comma, week equals, and we use a function called as.numeric, and it's going to say, hey, that week variable, that's a numeric variable that we want it to be read in as. So if we run this whole thing, you're going to see, notice how right now they're all shifted to the left of the column right now. They're going to move over to the right, and it's going to be read as a numeric variable. So we go and run that, grow long, and voila, now week is being read as a numeric variable. And we can do structure, comma, grow underscore long, and we'll see the week is now being read as a numeric variable. So we went ahead and we fixed that. So that's a pretty essential thing that if you're ever going to be working with random coefficient modeling or multi-level modeling or repeated measures even, your data set oftentimes is going to come in a long format, and you're going to be able to switch it over to a long format so you can perform the analysis. because now this is in a format that we can actually perform an analysis on. So I suggest just kind of playing around with the pivot longer function and just seeing what happens when you change things and what errors it throws at you. And then you'll be able to kind of figure out what's going on with the pivot longer function. You can change some of the names here and see what happens, but that pivot longer function is going to be the key to running these types of analysis. Okay, so we've done that. I gave you kind of a description of what each thing in the pivot longer function is doing. Then we're going to go ahead and describe our data set. So let's go ahead and do hashtag describe dataset. So insert new R chunk, and then we're going to do describe, and it's going to be the grow long dataset that we're describing. Go ahead and describe grow long. There we go. So the main focus we want to look on is this perform variable. So this 4.9 is going to come into play later. This is the grand mean of performance over all conditions. Okay, and we have a minimum of 1.27 to 10. So the range of possible values was 1 to 10. So no one got a low score of 1, but 1.27 is the low score that someone received. Okay, so I think next what we're going to do is we're going to go ahead and visualize the data. So the first thing I want to do is I want to visualize the amount of variation between participants and within participants. So that's meaning creating a box plot for each individual value in which we color it so that each kid has, we show what their range of scores is throughout the week. So the way we do that, we're going to create a box plot for each individual child. So let's go ahead and do that. So we'll do hashtag visualize data, and do hashtag plot change in performance for each kid. Insert in our chunk. So we're going to do ggplot, and then it's going to be grow long underscore long comma aesthetic. So our y is going to equal perform, so we can have some vertical box plots. Our color is going to equal, we're going to do something called factor kid underscore ID, and that's so that it reads it as categorical variable instead of continuous variable. Because as you can see, kid ID is read as a numeric variable. We want it to categorize it so that each of these is read as a category. Then we're going to do geom underscore box plot plus, we're going to do theme, and then we're going to do legend dot position equals quote none, and that's going to make it so that we just don't have a legend associated with this. Otherwise, it's going to give us a legend with, like 100 different values to it, and we don't want that. And then we're going to do labs title equals quote how much do subjects vary across week and each other question mark. So we go ahead and play that, and it should work out. It takes a little while to load this one. There we go. So we got a nice looking box plot. So what I want us to notice here is that there's variation between both within subjects and between subjects. So some subjects are scoring higher on average than others. Some subjects have little smaller box plots, which show that they didn't have much variation in the change of their scores from weeks 0 through 6. Some individuals had outliers and so forth and so forth. But there's a lot of variation between subjects here in the box plots that we've plotted here. So let's see what we got next. Got one more visualization for y'all. So this next one, we're going to actually be incorporating condition and seeing if there's a variation between condition. So the way that we do that, we're going to do hashtag plot line graph to compare conditions over time. Insert a new R chunk. Okay, so we're going to be doing this group by function, right? So we're going to do group, or I'm sorry, we're going to first do, grouped underscore week EX. So we're going to be grouping it by week and treatment. So we're group underscore by. We're going to do grow underscore long, comma, week, comma, TX cond. And then we do mean perf TX, mean underscore perf TX. So we're creating a new object called mean perf tx, which we're going to summarize our grouped weak tx treatment, comma, we're going to do mean perform, comma, na.rm equals true. True. And then we're just going to do mean perf tx, and then we're just going to do ungroup. I just like to ungroup it just so that it doesn't give us any problems later. Sometimes you have some problems if you work with a group data set. And then we're just going to go ahead and ungroup it. So I'm just going to run that first and make sure we don't run into any errors. Okay, looks like it worked out okay. So we have this group data set. So it looks the same, but it's grouped. Then we're going to go ahead within the same code chunk. We're going to go ahead and plot the data. So ggplot. We're going to do mean underscore perf tx, comma, aesthetic x equals weak. So this is where it's good that we converted that weak into a numeric character so that we can visualize it. Y equals perform, and then comma color equals as dot factor txcond. And that's again because if we don't do that, so txcond is going to be read as a numeric variable, and we want to split it into treatments 1 and wherever it is, treatment 0. So plus, we're going to do a geom underscore line. No need to fill anything in there. And then we're going to do scale x continuous. We're going to do limits equals c 0, comma 6. So that's setting the limits between 0 and 6, comma breaks equals sequence, comma 0, comma 6, comma, oh, that's an O, so 0, comma 6, comma I equals 1, plus labs. We're going to set some labs for our data set, for our graph as well. Title equals, quote, does performance change across week? And then we're going to do a comma subtitle equals separated by condition, comma, then we're going to do y equals, quote, performance, comma, color equals, quote, treatment condition. And that's just going to set it on our legend that instead of txcon, it's going to say treatment condition. Okay, so I think we got that all right. I'm going to go ahead and just enter this down so it looks a little nicer. Okay, so we'll go ahead and do this. Now let's go ahead and press play. Oh, it is. Let's see here what I did wrong here. Tx y equals perform. Oh, I forgot to name the. Sorry, so we're going to do perform equals. So you go up there and you change that to perform equals, and then it should work now. There we go. So there we go. All right. So sorry for that little hiccup there, but it's just so you know your summarize function should look as so. So it's perform equals rather than just the mean equals. I forgot to name the variable that we wanted it to be. Okay. So what do we have here? We have a graph that shows the difference between treatments. So as we can see, it seems like those in the treatment condition, so condition equals 1, are appearing to have, on average, higher scores as compared to those in treatment 2. Both, in fact, in treatment 2, going from 0 to 1, there's a decrease, and then it seems like it increases as well. Okay, so looks like, and we're going to be testing for this later, saying is there a significant difference between our treatment conditions later, but it looks like here, it seems like, yeah, it looks like there might be a difference between the two. So let's go ahead and look at our PowerPoint next and see what we got next to do. Okay, so we're going to be today working with a function called the lmer function, and this is essentially to run a random coefficient model or a multi-level model. We'll be doing it next week with our multi-level models as well, but essentially it stands for linear mixed effects regression, is this lmer, and it's similar to the lm function, which we do the outcome variable indicated by tilde. But then we also have this thing in parentheses in which we indicate what the random effects are. So we can put in a random intercept, we can put in a random slope if we'd like, and anything within the parentheses is as part of the random part of the equation. Anything to the left of the parentheses is considered the fixed effects part of the equation. So these are things that we're looking at the differences on average between or something like that. So, and then we do RML equals false. That stands for restricted estimated maximum likelihood. We're going to set that to false just so we have the simplest equation. And then we set our data set. So it looks very similar to the lm function. Additionally, this is essentially what we're going to be looking at today. Is we're going to be running a bunch of different models, and they're going to be looking like this, essentially. We're not going to graph them out. In fact, next week when we do multi-level modeling, I'm going to teach us how to graph them out. I just figured that for this week, we're just going to run the equations just so we get a feel of what's going on. But whenever I say that there's a random intercept that we're incorporating in, it essentially means that it looks like this picture. Notice how the slopes are all the same, but people start at different intercepts, right? So there's different intercepts in the way that people cross zero. If I say there's a random slope, it means that all the slopes to each individual is different. And then this red line in the middle, and then if we have a fixed slope, it's this red line in the middle, which say, what's the average slope that somebody has? And then you can also have random intercepts and random slopes models, in which individuals have random intercepts and random slopes as well. So each individual gets their own slope, and then we can test what the average slope or random or average intercept is between all those individuals. So a random intercept would be the combination of all these intercepts and saying, what is the average intercept that someone has? And then an average slope would say, what's the average slope that someone has overall? So right here would be your average intercept, and this line here, this red line here, would be your average slope. So with that, we're going to go ahead and be plotting a different model. We're going to start with a random intercept model. Then we're going to add in a fixed slope. Then we're going to add the fixed slope, random slope, and random intercept model. In which case, this is what if a random intercept and random slope model looks like. This is what just a random intercept model looks like. So let's go ahead and we'll do that. So what we're going to do is we're going to specify one part of our model, in which case we only indicate the random intercept here. So we're going to start off with just indicating a random intercept in our model. So to do that, we're going to do hashtag fit models and do hashtag intercept only model. So let's go ahead and insert in our chunk. We're going to name this grow mod 1. Use an assignment operator. We use the lmer function, not lmer function. Our outcome variable is perform regressed on, in parentheses, 1 by kid underscore ID. So what we're saying here is, do kids, because they're based off their kid ID, do they vary in their scores on the performance? We do data equals grow underscore long, comma, REML equals false. Okay, and I'm going to go ahead and change this so that's grow mod 1. And then we use the summary function to simply output our model, grow mod 1. So what we do, I'm going to go ahead and run this first. We get a new object in our data set that says object with null position. That's okay. It's just a list of all these coefficients for us. And we're going to use the summary function to output that list in a way that's readable for us. Oh, don't know what that is. Let's just run that one more time. Okay, I don't know what that should be fine with that error. I think it's something because I looked at it or something like that. But essentially, what we're saying here is that we get so this is this output that you should have on your screen as well. So what we're saying is that we get this random effects part of our model, in which we say the random effects, and we have random effects for kid ID because we set kid ID as our random intercept. And what we're saying is that those kids' intercepts vary on average by a standard deviation of 0.889. 8899. So what we're saying is their slopes, so you can imagine something like this, their slopes on average vary by 0.8899. So where they start off at performance 0 is varies by a standard deviation of 0.8899. Additionally, we have this fixed effects part of our model too, and we get an intercept as well. Now the intercept, in the absence of any other fixed effects, is just the grand mean. So we got a grand mean of 4.9, and if you recall, if we go back to our meaning, 4.90 was our performance grand mean. So in the absence of fixed effects, our fixed intercept is just the grand mean. So that's really it. So now what we're going to do is we're going to be making this model a bit more complex, and we're going to add a fixed slope now. So let's go ahead and add a fixed slope. So it's going to look just like our other model. So we're going to do hashtag add a fixed slope. We're going to do in our chunk, and then we're going to name this grow mod 2. Use an assignment operator. We use the lmer function. We're going to do perform regressed on, and our fixed slope is going to be tx condition. So we're going to say on average, does our treatment condition, which is tx cond, are they significantly different from each other? Plus, then we do our random part, which is 1, which is just like a placeholder for your fixed slope, for your random slope, kid underscore ID, comma, data equals grow underscore long, comma, REML equals false. We do summary, grow mod 2. And we run that, all that, and there we go. So what we get here is we get some more output again. And what we say, okay, let's look at our random effects again. So we're saying kid ID, so on average, with the presence of this fixed slope, kids' intercepts vary by an average of 0.8244. Then we also have a fixed effects part of our model, in which we say, okay, what's the intercept? The intercept here is when all of your fixed effects are at 0. So the average intercept for individuals and treatment condition 0 is what we're saying. So those that are in the control condition over here, and it's significant, saying it's significantly different from 0. And then we're saying going from treatment 0 to treatment 1 is associated with a 0.67 increase in performance. So, and that's significant and different. So being in treatment condition 1 is associated with a 0.67 increase in your performance score. So if we can imagine this, we can go back to our slides here. This essentially is saying they all have different intercepts here, and then there's an average slope for those in treatment condition 0 that is associated with, that would be going upwards, saying on average the treatment condition is associated with a 0.67, I forget what the actual thing is, but 0.67 slope associated with them. But people have different slopes that vary on average by 0.8244 standard deviations. So notice that it's standardized. Okay, so then the next thing we're going to do is we're going to make it a little bit more interesting, and then we're going to add in a random slope. So the way we add in a random slope is we do 1 plus, and then we put what our random slope is going to be, and our random slope here is going to be week. So we're saying, do people vary on average in their slopes by week? Is what we're saying. So are people progressing at a different rate? So to do that, we do hashtag add random slope. Then we're going to do insert in our chunk. Then we're going to do grow mod 3 assignment operator. And then we're going to do lmer do perform regressed on tx cond plus the tx cond is still our fixed effects, 1 plus week. So we're saying, do kids on average, I'll go ahead and bring this back, do kids on average, do they differ in the amount that they change over the week between each other? We do kid underscore ID, comma, data equals grow underscore long, comma, REML equals false. Then we're going to do summary, grow mod 3. So we go ahead and play that. Okay, so we went ahead and got our results here now. So I'm going to go back to the PowerPoint and show you what each of these averaged. So now it's saying on average, so we have our random effects model that we're going to look at first here. We're saying on average, while incorporating our treatment condition and week, the intercepts vary by 0.6791 deviations. Additionally, our week is saying, okay, and kids have different slopes going across every week. On average, those slopes vary by 0.2404 standard deviations. And then we also have our fixed effects model portion, in which we're saying the intercept for kids in treatment condition 0 while incorporating the random effects is 4.448. And then our TX condition is the average change of moving from TX condition 0 to TX condition 1. So it's associated with a 0.35 increase in your performance score. And these are each significant at a p less than 0.05 value. So let's go look at our images here. So what we're really looking at a graph that looks like this essentially. We're saying, okay, so all these kids have different starting intercepts. So what their score is at performance 0 would be there. They all have different things, and they additionally have different slopes associated with them too, based on their week as well. So their week is changing across the way that their slope is changes across week that they do. So we're saying that essentially there's differences in the way that their slopes go because we added in this week variable. Then what we can do is just to confirm that we're building the best model, we can run an ANOVA in order to see what the best model is. So let's go ahead and do hashtag compare models, and then we'll do insert an R chunk. It's going to be ANOVA grow mod 1. So we start off with the simplest model, then we go into the second most model, mod 2, and then grow mod 3. And we simply run that, and we're just really here just testing to say, does adding in this first with grow mod 2, adding in the fixed effect, does it really significantly explain more the variance and outcome of perform, which is our outcome variable? And then with grow mod 3, we're saying, does adding in the random effect of week, which is testing to see do people have different slopes across week, add significantly more variance and explanation. And essentially we could say, yeah, it seems like they are. So essentially going from grow mod 1 to grow mod 2 explains significantly more of the variance in our outcome variable. Going from adding in the variable of week from grow mod 2 does seem to explain significantly more of the outcome and why. So it's a good thing. What we're saying is that essentially, yes, this is incorporating a lot to our model by adding these in. And that's really all I have for you on random coefficient modeling. Next week, we're going to be discussing multi-level modeling as well, in which case we'll be adding on to this and just looking at a little bit different way of how to multi-level model, which we'll be comparing people in different groups essentially. And I think if it's confusing this week, multi-level modeling builds upon it. And I think it's going to make more sense when we do multi-level modeling. I'm going to be teaching us how to do some more graphing as well when we start doing multi-level modeling. Okay, so with that, what we can go ahead and do is I have an assignment for you in the Module 8 lab. Module 8 assignment. Go ahead and get started on that and let me know if you have any questions. Thank you so much.